reminds me, I used to take an exercise and stupidity. I used to take my math test in pen.
That's aggressive.
Yeah, my math teacher in high school told me, you need to stop taking your math test in pen because if I see one more scribble on
Right.
the page, you're getting an F on the test, I don't care.
You can't see it.
Yep.
All right, well, thanks for coming. I know that this is probably not how you'd originally envisioned spending your Friday evening, so hopefully we'll make it go as quick as we can while still covering what we need to cover. As I said, the test is open book, open note. None of you have taken a Barnes test before, right? The goal is not to ask you things and have you answer them all correctly and make yourself feel good. I envision tests as an experiment, okay? I'm trying to measure, here's 100%, here's 0%, okay? I'm trying to measure what you know, and in order to measure what you know, I need to also measure what you don't know. So my ideal distribution is going to peak somewhere around 50% because that maximizes my ability to discriminate between what you know and what you don't know, and who knows more and who knows less, okay? So I'm just saying, if you walk out there and you think you got a 60%, you're probably in an A- range, okay? That's a Barnes test, okay? So I'm just to warn you, don't freak out. Don't think like you're gonna have to like retake this test, this course or anything. That's normal. I expect for.
It's normal to feel that or normal to retake it?
It's normal to feel that. I mean, sometimes people fail my tests, but that is not actually most people. I mean, in a case like this, I expect to get like, we got 13 people in class. I expect like six A's, 6 B's, and probably someone didn't sleep the night before and is going to get like a C or a D. That's kind of like what I expect the final distribution to look like. But the raw numbers are going to be like low compared to what you may be used to from high school, okay? But you're not in high school anymore, so it's all cool. All right. I did write the exam, so there's 3 total questions. Well, there's 2 problems basically, which. Let's see, there's one problem on Lagrange, there's a Lagrangian problem, okay? I think I've said that many times. There's a Lagrangian problem. You will not be surprised by this. There's another problem, and then I used to have a second Lagrangian problem, and I'm getting cold feet, so I decided not to do that this time. And I added some small short answer questions, like qualitative or quick calculation kind of stuff, to more broadly cover some of the earlier chapters. Those should be pretty quick. So there's like, each of the problems has 3 subsections, and then there's the 4 sections in the middle of the short answer, right? So each of those subsections should take 1/10 of your total time, right? It's a 50-minute exam, so each of those should be about like 5 minutes. So, I mean, you could spend a little longer on there, but like if you spend 15 minutes on like the first subpart, you are gonna fall behind, you're not gonna make it. So make sure that you sort of budget your time wisely and that you've thought ahead, and you make sure you don't leave points on the table, because it could be that if you just wrote down, the obvious equation for part B of the 3rd problem, you could have gotten 3 points or something. Instead you're working on to get, figure out your minus sign error some other place, and you're going to spend 10 minutes on that when I'm probably only going to take off a point if you had a minus sign error. Usually the problems are bigger than that. So try to use your time where you can maximize your total points. That's part of the test.
So it's 3 main problems and like 4 short answers?
2 problems. The way I've split it up is problem 1 is the Lagrangian problem. Problem 3 is another problem. I'm not going to tell you what it's about. Problem 2 has 4 subparts where it's like little other problems, and so that's kind of what the rough geography of the exam looks like. I will tell you that we've spent the last couple of weeks on the weird stuff, starting with Euler-Lagrange and the calculus of variations, and then we started talking to use that when we started talking about what we're going to minimize. We started minimizing the Lagrangian. When it comes to Euler-Lagrange without the Lagrangian, what could I possibly ask you that you could answer in 15 minutes the shortest distance between 2 points? And you guys have answered that like 12 times already. So I am so sick of that problem, I'm not gonna ask you that. There's not a separate Euler-Lagrange problem. Euler-Lagrange will be tested in the context of the Lagrangian, so you'll be able to answer, there's a Lagrangian problem for which obviously you need to know the Euler-Lagrange equation, how to solve it and what it's solving. But I'm not gonna ask you the shortest distance between 2 points, which is honestly the only thing I could possibly ask you in an exam setting. So it just wasn't interesting enough to be worthy of my time. Nor yours, I suspect. Okay, so I figured I'd probably just go through what we've been doing. And I wanted to go through backwards just because that's the way I've been thinking of it, because I just did that, so that's cool, okay. Let's back up. What are the 4 steps you should follow when solving a Lagrangian problem? What's number 1?
Write down.
Please don't make this one harder than it needs to be. This is just, hey, there's 2 particles, so it's 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Okay, let's make sure we get them both, okay? So the goal here is to make sure you haven't lost an entire class of kinetic energy or potential energy. Not to make sure that you get v in, is that r theta dot, times cosine of omega or something. We're not there yet, okay? Start simple. Just 1/2 mv squared, maybe. Make sure you have all the different masses. If there's something additional going on, if there's like something rotating, if your mass is just sitting out there, if it's rotating, make sure you take that kinetic energy into account. Make sure you take all the kinetic energies. Make sure you have whatever potential energies you might need, whether it's 1/2 kx squared or whatever. The goal here is just to figure out broadly what you need, not to get the right answer yet. Then pick your generalized coordinates. Then rewrite the Lagrangian in your generalized coordinates. Now is when you go ahead and convert those into the complex part. This is the time. This is what you've been waiting for. Put it here. Not there. Here. Then last, solve the Euler-Lagrange equation. Which looks like what?
d over q equals d over dt, d over dq dot. Or some ends.
D by dt each. Well, whatever, yeah. 1q is fine. Whichever q it is you're looking at. Yep. Okay. So what problem should we apply this to? Let's I thought we'd do what I did on the other one. Apply it to the problem that I cut out of your exam because I had a temporary attack of mercifulness. So, and I admit it was pretty hard, okay, but I just wanted to see, I think you guys could have gotten pretty far. It would have been pretty okay. It would have been okay. But okay, this was the problem. You have a pendulum, you have a mass at the end of the pendulum, okay, but the string is actually a spring.
Jesus.
Good one, huh? Yeah. Yeah, this was totally not bad. Okay, that's the problem. What's the equation of motion? Okay, so how do we figure it out? Go through the steps. Use the steps. First step, write down the Lagrangian. Step 1, okay. What are the kinetic energies in this problem? 1/2 mv squared, yes. What is the potential energy in this problem? Minus mgh. You have to do both, okay? There is a potential energy both from the spring and from gravity, correct. You have to account for them both or you will get the wrong answer. Okay, number 2, what should our generalized coordinates be let's use theta. And R, maybe. I can't remember how I did this before, but it doesn't matter. It should work. Let's say but let's keep in mind that the natural length of this spring, or the equilibrium length, is L. So we can measure that length relative to R, relative to this X, which is relative to the equilibrium position. Okay, so we're going to use R and theta. Okay, step 3, let's convert these. What's V? Well,
R theta dot.
seems to me that there's two components, right? There's this bit and there's this bit. So I think there's an R dot and then an R theta dot. Yeah.
What about an R dot, theta dot? Cause oh, well, no, that's taken care of, the other R dot, isn't it?
R dot theta dot.
Cause it's gonna be moving back and forth and scrunching.
Yeah, so the R dot will handle the scrunching, and then the R theta dot will handle the penduluming. But of course, the final result is going to be some linear combination of the two. It's not going to strictly be one or the other, and that's where it gets a little bit hairy, I admit. But that's here. So the V squared is going to be R dot squared plus R squared theta dot squared. Okay, good. Minus mg, what's h? I think h is going to be just equal to minus r cosine theta. We'll measure it relative to the vertex in the center, just to get rid of that extra constant. So it's cosine theta equals 0. It should be equal to negative r. Yeah, that looks decent. Okay, so that's minus the minus r cos theta, but we're not done. We have a kx squared. Well, in this case, x is the difference from equilibrium, so that's going to be k times r minus l, quantity squared over 2. Just we'll minus that off. This is not bad. See? It's just like straightforward. Here's where it gets hard. Both of these lead to hideous, horrible, ugly Euler-Lagrange equations that are non-solvable analytically and are coupled. I mean, okay, that's just one of the many excitements for this problem. So let's go ahead. Who wants to do R first? Who wants to do theta first? Who is psychologically opposed to the concept of forcing us to use one of these? And should we do them at the same time again? Okay. I think theta won the vote. So let's do the first Euler-Lagrange equation. dl theta is equal to d by dt of dl d theta dot. Okay, thetas. There's one. This is going to be derivative of cosine is minus sine. So this is going to be minus mgr sine theta, I think. Plausibly. Is that not right?
That's great,
We're close. It's close. Okay, the next one is a theta dot. So looking for theta dots. I only see the one.
So it's 1/2 mr squared theta dot?
Without the half, because the
Sorry,
half
sorry,
should
yeah,
be out.
mr
So it
squared.
should be mr squared. Mr squared theta dot. The mass is constant, so we can pull that out front. But I have tragic news.
Radius is
Radius is not.
not.
So we're going to have to go all product rule on this guy. Okay, so negative gr sine theta is equal to 2r r dot theta dot plus r squared theta double dot. Is that right? Those of you that have been doing product rules more recently than me.
Oh, you did, oh, yeah, because you have to do a triple product rule.
Full-time derivative.
Yeah, yeah. I told you it would get exciting, so yeah. Okay, so theta dot times the derivative of r squared, which is 2r, times the derivative of r with respect to t, which is r dot. 2r r dot. And the other one's pretty straightforward, it's r squared and then theta double dot. Okay, so the theta equation, well, let's divide through by r, just, I don't know. Feels right. Minus 2r dot over r, and theta dot, minus g over r sine theta is equal to 0. Well, there's a theta double dot. That's not bad. That's the acceleration. There's a velocity term. Why is there a velocity term? Because, why do we think about this? Why is there a velocity term? Yeah, because as you swing downward, for say you're swinging this way, right? There's going to be a centrifugal term on the radius that's going to push the radius out, which is going to change the net angular momentum, right, and cause the whole thing to slow down. Ugh.
Should that be
Yeah.
plus 2r dot theta dot?
Okay, so this was on that side. You are correct. Absolutely right. Worse, it would be bad enough if this were just a theta, but it's not. It's a sine theta. So this, yeah, you're right, because we're moving this to this side, which would also be a plus. Yeah, no, you're on it. If we do the small angle approximation, which probably not good in this case, but if you were, you could end up with this, in which case you might have a soluble equation there if it weren't coupled to r. But it is, and there's a sign in there anyway, so this is not a solvable differential equation. But this is the numerical equation you would integrate on your computer to get to the solution in theta. Yeah?
So once we get to the solution, we just stop starting with the answer. We don't have to do this on the test like I actually do.
Normally, I want theta as a function of time. That is the equation of motion. That's what I want.
Right.
You can't do that with this. Okay, I'll tell you. There's not a whole lot of kinds of differential equations I expect you to be able to solve. The actual ones I expect you to be able to solve, especially on an exam, are going to be ones that end up as a polynomial, the ones that end up as an exponential, or the ones that end up as a cosine. Those are the ones I really expect you to be able to solve. Anything else is beyond my expectation. So if you can do that, but I'm circling this as if you were done, but you're right. What I really want to know is theta is a function of time, but that's not, in this case, that's not solvable, so that's why I stopped here. On your exam, you should not. You should continue on. Give me the equation of motion, which is the position in your generalized coordinate as a function of time. You can leave it in terms of the generalized coordinate, though. But let's imagine what this would actually look like, right? If you actually let this thing go, it would like be all over the place. We do all sorts of cool stuff. Let's make one. I don't know. I think we'd do cool things.
That's a chaotic system.
I think it would be, just by looking at it. I bet at low energies it isn't. I bet it's just fine. Low energies it does something prosaic. But like if you give it some super bouncy thing, sometimes it's going to be in kinetic energy, and sometimes it's going to be in potential energy with gravity. It's going to be high. Sometimes it's going to be potential energy because you're going to shove the spring in or something, right? And all that's going to be interacting. And I bet it's more chaotic. When should it be the most chaotic? This is advanced. You don't need to answer this. I bet it's most chaotic when the pendulum frequency, root g over L, is comparable to the spring frequency,
Also, they're feeding each other.
which is root k over n, right? My instinct is when these are near commensurate, that's when things really go like crazy. Or maybe when they're near an integer multiple of each other. So if this is double this or something, I bet you get, that's just my instinct, is that's when you get the most crazy behavior. Whereas if these are widely separated, right, if the spring frequency is much faster than the pendulum frequency, then this is it's just gonna be a pendulum that oscillates like this. And similarly, if the pendulum frequency is really slow compared to, really fast compared to the other frequency, then it's just gonna go back and forth, and it'll be slowly changing its length as it goes, but that's not gonna do anything too crazy. But I bet if they're close, it's exciting. So someone should build one of those for Phys321 or something. That's your other homework. Okay, we only have half this problem. We need to do the R component, and it's just as exciting. R's. There's one, and there's one. Nice. So there's three different terms to the generalized force in R. It's going to be m r theta dot squared. What's that? Centrifugal. Centrifugal.
Yeah.
Centrifugal force. That's mv squared over r. Plus mg cosine theta. What's that? That's just gravity. Gravity's pulling you down. But there's another term, which is k r minus l r dot. Does that look right? You're going to take the derivative of this with respect to r. So it's going to be 2, we're just going to cancel this 2, times r 2k times over 2 times r minus l times the derivative of this. L is a constant, so it's not changing with time. R is, so that becomes an r dot. Goes up front, outside. That's exciting. And that's equal to d by dt of dl dr dot. So where do I got r dot? It's just this one. So that's just m r dot. Whew, all right. And doing that derivative, that's r double dot. Let's divide through by m. This m goes away, this m goes away, this becomes k over m. So this is the unsolvable equation in R, which is, the reason it's unsolvable, of course, is because it's coupled to the theta and theta dot, okay? By the centrifugal term, the pendulum angle term, and then this is just the spring term. So really, there's just three forces. The acceleration in R is a result of three forces: centrifugal, gravity, and the spring. So it's really, this really isn't as bad as it looks. Unsolvable as it is when coupled to the other equation. So, pretty ugly. Which parameters, sorry?
There's 3 parameters.
What do you mean by parameters in this case?
You got theta dot.
Oh, 3 different terms. Yeah. Bad. But in principle, if you supply r at time 0, r dot at time 0, theta at time 0, theta dot at time 0, you should be able to uniquely integrate this forward and figure out its solution at a different point in the future. That's the idea. Except that I bet it's chaotic in some cases, in which case you'd have to know its initial positions infinitely well to be able to get the right answer. Anyway, okay, so that's a way more complicated version of what I will ask you on the exam. On the exam, I will ask you a problem where I'm going to give you a physical setup, and you're going to have to figure out the Lagrangian by figuring out the kinetic and potential energies. You will have to determine your generalized coordinates. You'll need to rewrite this in terms of your generalized coordinates, and then you'll have to apply some Euler-Lagrange action. You're going to be able to do all those. be able to get the answer. What's the answer I'm looking for? The equation of motion. Does that look like what I've circled? No, that is position as a function of time. That's what I want. Okay. Questions about the Lagrangian stuff? I know it's different and it's weird, and it's like a whole new way to approach physics, and so it's a little complicated, it's tough. I'm not gonna ask you a question this hard on the exam anymore. I was going to, I was all excited about it. I'm checking it out, you have a nice easy one on the exam, but you need to show me that you're able to follow the steps, and you know what the steps means, and you're able to come up with a differential equation in the end, and then hopefully come to a final answer in terms of an equation of motion, position as a function of time. That one is not going to be easy, but it's at least straightforward, because I just told you what it is, mostly. The difference is going to be you're going to have to figure out the physical setup once I lay it out. Any questions about that? Or not? Okay. Number 6, chapter 6. That was the Euler-Lagrange stuff. We don't need to talk about that. We're talking about the Lagrangians. That totally encompasses that. What's chapter 5 about? Oh yeah, simple harmonic oscillators. Well, they permeate every bit of your life, so you should probably know about those. What specifically do you need to know? Well, I mean, like, what's the equation for a simple harmonic? What's the equation of motion for a simple harmonic oscillator in general? What are you guys looking at me for? I'm asking you. It's a review session, not a me reteach you everything session.
A cosine of omega naught t plus delta.
Minus, yeah. Okay. What do all those mean? What's the A?
Amplitude.
What's omega?
Frequency.
This is the frequency it's oscillating in, right? If it's a driven harmonic oscillator, this will be the driving frequency. If it's just a undamped, undriven oscillator, then that's the natural frequency.
Which is root k over m.
Root k over m if you're looking at a spring. Root g over l if it's a pendulum, for instance. If it's a damped oscillator, then that's omega 1, right? Which is omega naught, the natural frequency, but a little slower, modified by the friction.
What is the square root of omega squared? That's the damping parameter.
That's right. Minus beta squared, or just minus beta squared here. Yeah. What's this last one?
Phase shift.
The phase offset. So it just happens to be where you put the 0 point in a undamped, unforced oscillator. In a forced oscillator, of course, there's a second term, right? There's the transient term and the long-term solution. The transient term, you did a homework about that. I care about the long-term solution, okay? So in the long-term solution, the phase represents the phase between the driving frequency and the response frequency, okay? So if those are exactly in phase, then delta is equal to 0. When are they in phase? They're in phase when you're driving it much slower than its natural frequency, and it just responds right in phase, okay? If you're driving it much faster than natural frequency, it goes 180 degrees out of phase, okay? And then delta is equal to pi, or 180. If you're forcing it right at the natural frequency, where you're maximizing the amplitude, then they're 90 degrees off, and this is 90 degrees. Remember, I gave you equations too for figuring out the amplitude in this case, for figuring out the frequency You know the frequency in the driven case. And there's another equation to figure out the phase offset, right? So in a damped driven system where you know the decay parameter beta and the forcing, the amplitude of the forcing function, as we usually do it in acceleration space, and you know the forcing frequency and the natural frequency. Given all those, you should be able to figure out, you know, what the amplitude should be and what the phase offset should be in any given case. Okay? That's oscillators. Anything else about oscillators you need to know? List of juice figures, those are fun. Damping, driven, we talked about driven oscillators. You don't need to be able to solve this particular solution derivation stuff. You do need to know the parameters, how to figure out your parameters there. Fourier series. I love Fourier series. I'm really not going to ask about I'm not going to ask about it on the test. I'm going to be honest. Okay, so I think Fourier, being able to think in Fourier space will transform your life. It's like it really you just see things in a whole different way if you're able to see them in Fourier space, and it will help you in whatever career you go into. I'm not asking about a test. I'm just saying. I wish I could. Maybe we should, but I didn't. I'll be honest. Okay. Chapter 4, kinetic and potential energy with forces. Oh yeah, we're doing like line integrals, path integrals, right, to figure out what the total energy was that you'd use for a given force. And then we talked about conservative and non-conservative forces. How do you tell if a force is conservative or not?
Curl is 0.
Take a curl. If the curl is 0, you're good. If it's not, that saves you from having to, of course, calculate all possible paths, okay? Like one calculation instead of an infinite number. It's really a time saver. What else did we talk about in that chapter? That's boring. How do you tell if a system is, okay, right. How do you find the equilibrium points of a system? You figure out where the forces are 0. How do you figure out forces as a function of the potential? If you know the potential, how do you figure out the force? Yeah. Which one?
It's integral.
Nope.
Nope.
It's the negative gradient of the potential.
Oh, yeah.
Force is the negative gradient of the potential. Gradient is just, in one dimension, it's just the derivative, okay? If you want to figure out one in multiple dimensions, it's just the individual partial derivatives in Cartesian space. If you want to figure it out in non-Cartesian space, you look at the back of the book, and it tells you how to do it. Very last page, okay? Tells you how to do curls in multiple coordinate systems. It tells you how to do gradients in multiple dimensions. Use that page. It is your friend. So that's potentials and forces and stuffs. Yeah, okay. Any questions about that? Yeah, that's easy, right? Okay. Next one was about momentum and the center of mass. Of course, momentum is equal to P, mb, P, which is equal to mb. Oh yeah, here we had this problem where we did the triple integral to figure out where the center of mass was for a cone. So I have another one that I chickened out on. I was going to ask you to calculate the center of mass of a hemisphere. Yeah, that'd be cool. Okay. So like, right, so you take a hemisphere, like a snow globe, and a snow globe. I don't know why you're taking them. Want to figure out the center of mass. That's beyond the scope. Okay, so call that the origin. Call this the z direction. So like, remember that I was going to ask you this, but I didn't. Oh, you have guesses?
Isn't it like 2/3 or like 2 pi over 3 from the top of the hemisphere? About. Assuming uniform mass distribution of this hemisphere.
It isn't, but it's not far off. It's not 2/3 from the top, no. Okay, should we try and figure out then?
Yes.
Okay. All right, so recall how to figure out the location of the center of mass. Obviously, it's going to be at the origin in the xy plane down here due to symmetry. The question is where it is in z, so I'm just going to do the z integral. To figure this out, right, you take 1 over m times the integral of z dm. The mass-weighted position. Okay, so that's going to be 1 over m. We're going to integrate from 0. We're going to call the radius of this thing capital R. So we're going to go from 0 to R in z. And I'm going to add up a bunch of like we're going to make a bunch of separate pancakes, right? Okay, we're going to add up the pancakes, which each have a different radius. So the volume of each pancake is going to be equal to pi r squared dz. Multiply that by rho to get dm. We still have this z term that I haven't included. The trick is, what is this r? Well, that r is not big R, right?
That's a function.
Yeah, it's like that. This r. It's the radius from the axis. Well, shoot, how do you figure out that? Well, this is capital R. This is z. So r squared plus z squared is equal to big R squared. So solving for little r here, r squared is equal to big R squared minus z squared. So that's what we're going to put in here. Integral from 0 to r. I'm pulling the pi and the rho out because nobody cares about those. This r squared becomes r squared minus z squared. You got a z, you got a dz. Okay. I'm going to split this into 2 integrals by multiplying through here, okay? So we're going to integral from 0 to r dz of r squared z. And we've got a minus an integral from 0 to r of z cubed. Yeah? I don't hear a lot of affirmations from out there. Yeah? Vaguely? All right, well, I can even I can do those integrals. Pi rho over m. What's the integral of r squared z?
Take it all the way to the front.
Don't get ahead.
Z squared.
Yeah, rz squared over 2.
R squared over 2.
R z squared over 2 evaluated from 0 to r minus, what's this integral?
Z to the 4th.
Z4 over 4, yep. Also evaluated from 0 to r. When you evaluate those things at 0, they're both 0, so you don't have to worry about that. The rest of this becomes r cubed over 2 minus, we blew it somewhere.
That should be r squared z squared.
Thank you, because these have to have the same units, so they have to have the same number of r's, otherwise something has gone tragically wrong. Okay, good. All right, so these both come out in meters to the 4th now, so I'm okay with that. What's r to the 4 over 2 minus r to the 4 over 4?
R to the 4.
Yep, r to the 4 over 4. Okay, that's the answer, but like we can do better than that, because we can figure out the mass. What is the mass of a hemisphere?
Rho times volume.
Rho times the volume. What's the volume of a hemisphere? What's the volume of a sphere?
4/3 pi r cubed.
So,
It's 2/3.
yeah, half of 4/3 pi r cubed.
2/3
So 2/3 pi r cubed. Yep, that's what I think. Okay, so let's plug that in for m. Pi rho r to the 4 over 4. For the m, we have a rho, a 2/3, a pi, and an r cubed. Okay, so the pi's are going to pop, the rho's are going to go away. This r cubed will get rid of all those, 3 of those r's, leaving with just with an r. See how I just canceled the exponent? Don't try this at home. This is advanced canceling. Okay, and we're stuck with 3r over
It's 3 over
8. So that's why I said it was close to 1/3, but that would be 3/9. So your instinct was on the money. It was not too far off, but that's the actual answer. See, you guys totally could have done that, right?
Yeah.
Yeah. See, maybe I should have asked it, but I think it would have taken you longer than I wanted to expend on a center of mass problem, and that's kind of why I didn't ask it in the end. But I totally think you guys could have done that. But there you go. No, I didn't end up talking about that. Angular momentum. Everyone's favorite momentum. Yeah, okay. What is chapter 2 about? Chapter 2 is about, air resistance. So, right, we talked about the 2 different drag terms, which are,
The Cole's drag.
no,
No.
quadratic
Yeah,
drag.
that.
Mhm.
Linear drag.
And linear drag. Right, and you take the ratio between them, you get the Reynolds number to figure out which one's important in any given case. Quadratic drag trajectories, we talked about hyperbolic tangent solutions, but it's kind of advanced for asking a 15-minute question on a test. We talked about how charged particles move in magnetic fields. How do they move? Did it just go?
Seems we're in that class right now.
V cross, the velocity cross the magnetic field.
Okay, the force is V cross B. So B's this way, and V is this way. And that V cross B, you're gonna have a force that's this way, unless it's an electron, in which case it'll be negative in that direction. So let's do that. Okay, so they move in circles around the B field, well, actually spirals, right? Because they're gonna, if they have some net direction in the Z direction here, they're just gonna keep going. So they're gonna spiral around the B field with a radius equal to the gyrotron radius. So I have that in here. mv over qb looks like. Stuff like that. I was just asking, we just talked about that just to show how things get complicated, and they do. So you guys are in 341, right? So you should know that. You should be able to have that. You talk about, see? Thing is, we spend 1 day on them in each class, right? You know, so I don't know if we need to spend more than that, but like Fourier transforms are awesome. They're really great. I love them. Chapter 1 was boring. I was just trying to intimidate you about different coordinate systems. It wasn't that important, I don't think. Anything you think I didn't talk about that I should have?
So,
Any questions you might have about other stuff? Anything? All right.
We guessed the other, like, long answer problem. Will you tell us if we're correct?
No.
Is
You
it
could ask.
not
Can we sit
Lagrangian?
here and play the guessing game until we get all the
And then you can look at
questions and answers to the exam?
Then you can just look at my poker face and see if I have a tell. You can try that.
Is it not Lagrangian?
No. It is a non-Lagrangian problem. I already said that though, so that's not.
Could we use Lagrangian to solve the problem as well?
I don't think so.
Probably gonna be a pain in the ass if you can't.
I think, yeah, I think if you could, you probably would not want to.
Leaves and exercise 3.
Okay. We will, good luck. You guys have a week to study, so hopefully it'll be all right. I will be in text contact for the exam, so talk to Stephen, who will be proctoring, and he'll be able to get in touch with me if anything else.